Let's resume our sedimentary lecture by discussing the principles of stratigraphy and types of unconformities or breaks in the rock record that we might see. Sedimentary rocks form on Earth's surface. We've already discussed that. And implied within that is that new rocks must form on top of older rocks, at least with those sedimentary rocks. If they're forming on Earth's surface, they're on top of what was already there, which must be older rocks once you dig down far enough. This allows us to use the arrangement of rock layers to determine which rocks were placed in which order, especially if we're dealing with sedimentary rocks. But as we'll see, we can use these same principles to apply to other rocks if we're careful. And those rules that allow us to use that arrangement of rocks are called, in general, principles of stratigraphy, which refers to the layering or strata of rocks. Might also be called Steno's laws, after the very early geologist that first started to come up with some of them, named Nicholas Steno. So 17th century geologist, is 1600s. This is old stuff. And he first started to come up with these ideas of the principles of stratigraphy, at least some of them as he knew them at the time. And so sometimes you'll see the principles of stratigraphy also called Steno's laws. Should know both names. So these principles are the law of superposition, the law of original horizontality, the law of cross-cutting relationships, the law of lateral continuity, and the law of faunal or fossil succession. He didn't come up with that one. That one came out much later, once we started to understand the fossil record in the context of evolution. Let's talk about what each of these mean. So the law of superposition means that young layers sit on top of older layers, at least once they form. So this describes when rocks are flat lying and you see A, B, and C, you know A must have formed first, B formed second, and C formed last. The law of original horizontality states that sedimentary layers are originally deposited flat. Gravity wants to pull these layers down flat and wants to pull the faces of beaches as flat as it can. When it causes sediments to settle out of solution, it does so and makes a relatively flat layer of them. So that if you were to find rocks that are tilted or folded, the tilting or the folding happened after the rock formed. So we can say that it happened later, after the rock was deposited. When these rocks were deposited with this configuration here, they were originally flat, much like this one up here. They were only tilted or folded later. That's the law of original horizontality. Right? You can get that by breaking down the name. The rocks were originally horizontal. The law of cross-cutting relationships says that any phenomena that cut across rock layers, like intrusions of igneous rock or like faults, those cuts must be younger than the layers that they cut across. Otherwise, how would they have cut across anything when they formed? Right? So if you see rock layers and then something crossing both of them, you know that C in this case must have happened after both A and B because it cuts across both. The law of lateral continuity says that rock layers originally spread out about as far as they could, which is until they hit a solid boundary or run out of material. And we'll see how that applies to things like the Grand Canyon that's got the same rocks on both sides, and even rocks that are really far away from the Grand Canyon that are the same as the rocks in the Grand Canyon. It's pretty cool. The law of faunal or fossil succession is how we can use fossils to correlate ages of distant rock layers, because those organisms only existed at certain times. Once an organism appears, it could in theory spread everywhere. It doesn't always, but then once it disappears, it's gone extinct and it's not coming back. That's the basis of the law of fossil succession. So let's illustrate each of these. Law of superposition. If you took some sand, different colors, and you just dumped it into this beaker here, And all I gave you was what it looks like at this point. You didn't know what order we did them in. You could pretty easily be able to determine, well, you poured this one on top at the end, so brown was last, red must have been in the middle, and yellow was first. Yellow was oldest, then red, then brown is the youngest. That's all the law of superposition is, and we use that to do a lot of work in stratigraphy. We can look at the rocks like we have in the Grand Canyon, and here are the names of some of those layers. So nice picture over here, broken down over here. So Kaibab limestone, Toroweep Formation, the Coconino sandstone, the Hermit Shale, and then the Supai group underneath. Well, the law of superposition we can use to tell us the Supai group is the oldest, followed by the Hermit Shale, followed by the Coconino sandstone, followed by the Toroweep Formation, the Kaibab limestone being the youngest one. That's what we use the law of superposition to tell. The law of original horizontality says that any of the folding or tilting that might be visible in these rocks, it's hard to tell just what from this picture, must have happened after they formed. That originally these layers are deposited flat lying, and that only later does any deformation happen. The law of cross-cutting relationships, I'll illustrate here. And we had said that things that cut across other things must be younger than those things, or else they wouldn't have had anything to cut across. So judge for yourself, looking at this somewhat complicated picture, but which really is pretty common when you look at the geology out west. Which sequence represents the order of deposition in this cross section from the oldest to the youngest? Because the blue dike and the red pluton cut across a bunch of things, right? These are igneous rocks. So the principle of superposition isn't going to help us much because they can form from below. So we're going to have to use the law of cross-cutting relationships. So if we're looking at this, we have F, D, C, B, all of those are cut by both the pluton and the dike. So since our answers are only dealing with F, D, and B, we know that it must have been F, then D, then B. And then the other two things happened. Now, what order did they happen in? Did the pluton form and then the dike? Or did the dike form and then the pluton? Well, we can see that the dike cuts across the pluton, so the dike must have been last. Must go F, then D, then B, then the pluton, then the dike. And then A cuts across both of those, so A would have happened last. Otherwise, this pluton and the dike would have cut across A. So the law of lateral continuity says that rocks that are very distant can be correlated with one another. There might be the same rock because when sediments spread out, they spread out as far as they can under the constraints of unless you hit a solid boundary like another coastline or unless you run out of sediment. So a lot of the rocks that we see in places like the Grand Canyon continue very far away, and they certainly continue all the way across the canyon, so that when you look at the canyon today and you see a layer of rock here, layer of rock here, layer of rock here, at some point, they used to be contiguous with one another. And you can guess that on top of this brown rock over here, on top of this, I guess, Mesa Verde, oh yeah, that's supposed to be Mesa Verde Formation. On top of the Mesa Verde over here, you used to have Wasatch, but it's been eroded away. You can see that pretty strikingly in places like the Badlands in South Dakota with these very colored bands on the rocks that make them up that are still pretty flat lying. And you can see that white band that's here, that's here, that's here, continues all the way to the rocks in the distance, right? These over here, even maybe these over here, it's hard to tell from here. But that same banding pattern reflects the sedimentary rocks themselves and how far off they would extend into the distance if they hadn't been eroded away. fact, this is really cool. If you look at these 3 national parks out west, starting with the Grand Canyon, going through Zion and up to Bryce Canyon National Parks, the rocks in them correlate with one another. At the top of the Grand Canyon, you have the Kaibab limestone and the Moenkopi Formation. Those are actually the bottom rocks that you find at Zion National Park, hundreds of miles away. You can see the map over here, right? So we've got Grand Canyon, Zion, Bryce Canyon. So these rocks extend over this whole area, much of southern Utah and northern Arizona, because they formed in an environment that was consistent across all of those locations at the time. Right? Then you have more rocks, Navajo Sandstone and Carmel Formation, that continue over here. And if you were to dig down in Zion, down below the ground, what's the rock that you'd hit after the Kaibab? You'd probably hit some Toroweep. Not 100% sure, because maybe it didn't extend that far. Maybe it ran out of sediment. And the Coconino. But at least gives you a guess as to what's going to be underneath this, because these rocks are contiguous if they can be. Lastly, the law of fossil succession states that fossil organisms appear and disappear in the rock record in an orderly fashion. And it's a major tool that we use for dating and stratigraphic correlation by looking for things like what animals existed at a time and allow us to say, okay, if this rock has trilobites in it, it must be of some age when trilobites still existed at Earth's surface. If the rock has dinosaurs in it, it must be from the Mesozoic, because that's the only time that the dinosaurs lived. Let's talk briefly about unconformities, which I mentioned before. Unconformities are interfaces, surfaces between rock beds that represent a break in the rock record. And these are caused by erosion or non-deposition for a long period of time. There are 3 types that we'll talk about: angular unconformities, nonconformities, and disconformities. So as rocks are being laid down, like let's say within the Bright Angel Shale, right? Like as these layers are being laid down, there's a little bit of sediment being deposited all the time. It might take thousands or millions of years to build up this whole thing, but the sediment is depositing here roughly constantly over this whole time. At some point, the environment changed, and maybe we moved to a shallow sea situation here, and that's why we're depositing limestone. But at some point, we might hit one of these irregular breaks. It's not flat, and it cuts into part of the limestone here, right? It used to be this tall, but it cuts down into it over here. This is a type of unconformity. In particular, we call it a disconformity, and we'll see why in a bit. There are similar unconformities with slightly different characteristics down here, right? The Uncar group has some slanted rocks. We know these used to be horizontal, so it must have been deposited horizontal, then tilted, and at some point eroded away to give this angular unconformity. We'll talk about what makes it angular in a moment. But the key is that these surfaces labeled in red here that tend to be irregular to some degree, they're not totally flat. These are all called unconformities, and they represent breaks in the rock record. Could be thousands, could be millions, could be hundreds of millions of years, where either no deposition was happening or rocks were being eroded away slowly. Okay, let's talk about what an angular unconformity is. An angular unconformity is one that records that there was deformation in between these depositional events that took those flat-lying rocks and folded or tilted them. And as a result, when you see an angular unconformity, the rocks, like here, are at an angle to one another. The ones below are tilted, the ones above are flat. There's an angle that you could draw there. So that's an angular unconformity. You might start with deposition of these flat-lying rocks. At some point, folding happens. Maybe you had tectonic plates squishing together, pushing on these rocks and folding them upward, causing those originally flat-lying layers to be bent. Then erosion happens, cuts down into the surface and leaves this irregular surface erosional surface that once we deposit new rocks on top of it that are again flat is a type of unconformity. And we can tell that it's angular because there's an angle in between the layers above and below. One really famous one is Sicker Point, Scotland, and it was a place where these early geologists, James Hutton, along with John Playfair and James Hall, really, they went a lot and they pondered how it could be that we had these different tilts to these rocks and realized that there must have been a long time acting in between in order to tilt these rocks after they were deposited, and then to deposit new ones, and then to even tilt those. This was one of the first places that geologists were starting to realize just how old the Earth must be for all this to happen. In this image, can you tell where the angular unconformity is? Take your guess. Take a look at it for a moment. So you're looking for a place where the rocks are one trend on top and then another trend below with an angle in between. So this roughly is your angular unconformity. Hard to tell whether it starts here or whether it continues down there, but this is pretty much where your angular unconformity is. Okay, so when we have nonconformities, that happens because igneous rocks can do weird things, right? Igneous rocks can form above or below, right? They can be intrusive or they can be extrusive. So that if you have igneous or really old metamorphic rocks involved, those surfaces must be nonconformities. And we have to be careful about age dating with those. And that's all it means, right? They can be relatively flat-lying. But because these igneous rocks we know don't form flat like other ones do, especially not the intrusive ones, when we see that, we know that there must be some time missing. It turns out in this case, if we went back and looked at it, this rock had intruded underneath some sedimentary rocks. Over time, all of that had eroded down to a relatively flat layer, and then new sediments were deposited on top of it. So in this case, you've got basalt, and then you've got some sedimentary rocks up here. You call the surface in between these a nonconformity. Once again, it's a type of unconformity, which means that there's a break in the rock record there. Disconformity is sort of the simple one. It's a flat-lying sedimentary layers above and below. There's just an irregular surface breaking them up, and that irregular surface, where it cuts into the older rocks a little bit, lets you know that erosion must have happened, which means that there's a break in the rock record, right? If erosion happened, that means that some of the rock was moved away. And that means that it wasn't being deposited at the time. So it's a type of unconformity because there's a break in the rock record there. Here's sort of a micro disconformity here, where we see ancient soils, maybe some floodplain deposits mixed in, right? And then they get cut into by another flat-lying rock, but that clearly that surface cuts into the old Paleosoil horizon. Otherwise, the soil horizon would have continued across here. What that tells us is that over time, these sediments were laid down, a soil formed here, and then a river channel cut that soil as it was there, eroding some of that rock, removing some of the evidence of that Paleosoil that existed over here, and indicates that in between these layers below and these layers above, there's time missing. This is your disconformity. So, which of the types of unconformities is clearly shown by this picture? Should be fairly easy to tell. The rocks down here are at an angle. The rocks here are flat. Since they look like they're both probably sedimentary because they form these layers, we can pretty confidently say that that's an angular unconformity. You'd want to be sure, so you want to go up and make sure that this wasn't a layer of basalt or rhyolite or something, in which case we could call it a nonconformity. But in this case, because sedimentary rocks tend to be the ones that form these flat-lying layers, it's probably angular.